You may be asked to linearize a function or write a linear approximation of a line, and you should be able to use this using point slope form. Y minus y1 equals m times x minus x1. First of all, useful to know that sine of 1 is approximately equal to 0.841. Of course, that's an infinite decimal, but approximately equal to that. I'm probably going to use sine of 1, though, when I make my substitutions to keep this in exact form. But as a result, I know that x is going to be 1. I know that that y value is going to be that sine of 1 value, which is approximately 0.841, and I just need the slope. Well, pretty straightforward. We know that the slope of a curve is going to be equal to the value of the tangent at that point. The slope of the tangent at that point. So f prime of x is equal to cosine of x. So the slope is going to be cosine of 1 at that point. Cosine of 1 is equal to approximately 0.540 should you need to make the substitution. And you can write this equation either as y minus sine of 1 equals the cosine of 1 times x minus 1. Or you could write it as y minus approximately 0.841 equals 0.540 times x minus 1. That's the linear approximation of that equation. Something else you might be asked to do, you might be asked to make an approximation of your function using your linear equation. Of course, if I'm going to do that, 1.1 would be my input, so I would have y minus 0.841 equals 0.540 times 1.1 minus 1, which would give me 0.0540 equals y minus 0.841. Okay? If I want to simplify that, I end up finding out that y is equal to approximately 0.895. And that's my final approximation. Another thing you could be asked is to find the error of approximation. So that's the approximation of sine of 1.1. Basically, you would find the difference between that value and the sine of 1. Of course, the sine of 1.1 would be the actual value. So I could find the sine of 1.1 and subtract that 0.895 approximation. And I get approximately negative 0.00379. The decimal continues, so you can see I'm only off by a very, very small amount. Other things I could be asked. I could be asked to solve for dy. Remember that we can say that f of x is equal to dy dx. I can multiply both sides by dx. Sorry, a little mistake here. This is f prime of x is equal to dy dx. So I can multiply both sides by dx, and I find out that dy is equal to f prime of x times dx. So I can literally just take the derivative of sine of x, which is cosine of x, multiply that by dx, and that is my value of dy. If I want to create a visualization of dx, actually a visualization of dy and dx for that matter, basically you've got a tangent line to a curve, and visually what's happening is you're looking at two different points on the curve, from the tangent point over to a second point. And the delta x, of course, is just the change in the x between the two coordinates on that point. That's the same thing as the dx. It's the change in the x for the tangent line. Well, delta y is just going to be the change in the y value from one point to another on the curve. The dy is going to be the change in the y value from the first point to the second point on the tangent line. So technically, if you find your dy value, you can subtract the change in y from your equation. Of course, in the previous example, dx, the change in x, I've gone from sine of 1 to sine of 1.1, so dx is going to be 0.1. Of course, the change in y would just be the change from sine of 1.1 to the sine of 1, and then dy, of course, I could find in my equation up here. So different approaches, but that's the basic visual as far as what you're doing in these problems.